Hello, today I want to talk about implicit differentiation. Implicit differentiation is very similar to ordinary differentiation, except we're not given necessarily y as some explicit function of x, right? This would be an explicit formula for y in terms of x, right? That is, y is equal to some expression that only involves x and not y. That would be an explicit formula for y. So here we're saying that this is not the case, that we don't have an explicit formula. Instead, what we have is we have an implicit, we have that y implicitly is a function of x, right? It's defined implicitly. For example, say x squared plus y squared equals 1. This is the unit circle, right? This does not represent a function, right? It fails the vertical line test. So it's not a explicit formula that gives a well-defined function, but you could think of y as a function of x on maybe little parts of this graph, right? You could imagine as I move the x coordinate here, the y coordinate changes, right? As I pick different x values, the corresponding y coordinate would change up on that top half. Or I could think of the bottom half as a function of y with respect to x, right? If I sort of zoom in on a little part of it, I could think of that as a function, even though it's really only given as an equation, right? And it in and of itself is not an explicit formula for y in terms of x. So this is what I mean by an equation. Something like x squared plus y squared equals 1. It's an equation that relates x and y, but not necessarily an explicit formula, right? So what is the idea here? The idea is that we can take our equation, right, that relates x and y, and like I described here, you can differentiate both sides with respect to x, treating y as some unknown function of x. So y here will not be treated as a constant, right? Y will be treated as some unknown function of x. For example, so this is not really part of the example. These are just comments on what's explicit versus implicit, right? But for example, let's look at an equation that relates x and y. So I want to consider the equation x plus y plus 2xy equals x squared plus y squared, right? Now, this is a claim that we know right away, this is a conic, right? Because it's a degree 2 polynomial equation in two variables, right? It's degree 2, and every quadratic equation this is a fact from algebra, right? That every degree 2 equation corresponds to ellipse, hyperbola, parabola, circle, or pair of lines, right? Sort of the degenerate case, right? So this is, well, or a point. That's a really degenerate case. But this is this one is pretty clearly not just a point, right? So it's if we look at this equation, because it's degree 2, it's either ellipse, parabola, hyperbola, circle, right? It's going to be one of those figures or pair of lines, right? But it's sort of hard to determine which it is because it's not in one of the standard forms that you usually look at in college algebra, right? So how could I start to analyze this? Well, I could start to analyze this by just plugging in some points and solving for some points on the graph, right? That's always a good place when you're graphing, whether you're doing a function or an equation, right? Let's start by just finding some points. I want to learn a little bit about this graph. So for example, if I set x equal to 0, what would I get? I would get y equals y squared, right? That's what I get if I set x equal to 0. All the x terms go away. And what does this mean? If y equals y squared, then I have that y minus y squared equals 0. So y times 1 minus y equals 0. So I get the two solutions to this equation are y equals 0 and y equals 1, right? That's the solutions there. So I have 2 points now. I have 0, 0, and I have 2 nice points to graph, 0, 0, and 0, 1. Those are now points on my graph, right? I could also say I set y equal to 0. That's also a nice thing to do, right? If I set y equal to 0, what do I get? I get x plus 1 sorry, I said 0 and my hand did not listen. So y equal to 0, there we go. And now I get x equals x squared once y is 0, right? And so the exact same algebra then will imply that x equals 0 or x equals 1, right? So that gives me some points on my graph. 0, 0, actually again, so that's fine. That point came up twice. We kind of knew it had to because 0, 0 was already there, and then we set y equal to 0. So we better have found x equals 0 again. But this also gives us a new point. It gives us the point 1, 0 on the graph as well. So there we go. We got a couple points on our graph. So nothing crazy, right? But we found a few points. And if you want to find more, you could find more by the quadratic formula, right? You could say I set x equal to 1, right? Well, I know I'm going to find this point if I set x equal to 1, but I'm probably going to find another, right? Let's do that. Setting x equal to 1 in this equation. All right, so x is 1, y stays the same, 2 times 1 times y. On the other side, I have 1 plus y squared. There we go. Right, and how does this clean up? Well, I have y squared. The 1's actually cancel, right? And then the other point here is going to be, or the other side of the equation is going to be 3y, right? So what does this give me? This gives me that 3y minus y squared is 0. So again, factor out a y. So what do I get? I get that y is 0 or 3, right? So I get the point that we knew about, right, for x equals 1, because it's this same point up there. So I knew about that point, but that wasn't the only point where x equals 1. I have this other point here, 1, 3. Right? I found another point where x equals 1. So I'm gathering just some points, and you could get as many of these as you want. You can keep plugging in values for x and using either factoring or quadratic formula to get corresponding values for y. Or you can do vice versa. You can plug in values for y and get values for x, right? But this, of course, gets tedious after a while. So let's graph these points, and then let's use derivatives a little bit to study this graph, right? So here, let's see what points I have. So I have 1, 3, right? X equals 1, 1, 2, 3, right? There's the point 1, 3. I have also the point 1, 0 on my graph. There's 1, 0. I have also the origin is on this graph, right? And I also have, what was the other point? 0, 1. Yeah, 0, 1, right? So 0, 1. So this is the graph that these are just some points on the graph that we're working with here, right? So now, but what does it do from here, right? It would help me really see the shape of this graph if I knew a little bit more about the rate at which it was changing other than just fixed points, right? And notice this is definitely not a function, right? Right here, it's failing the vertical line test. Here, it's failing the vertical line test, right? So I cannot, it's a valid equation, but not a function, just like a circle, right? A totally valid equation, but not a function. So I can't find the derivative by just solving for y and then doing ordinary differentiation. Instead, I need implicit differentiation. So let's now start to think about slopes. So let's differentiate both sides of our equation. So I have this equation, this x plus y, right, plus 2xy equals x squared plus y squared. And I want to take both sides and differentiate with respect to x. So I'm going to take the derivative of this side with respect to x, as well as the derivative of this side with respect to x. So some of these terms are easy. For example, this one is just the derivative of x. This is just an ordinary derivative. If you differentiate x with respect to x, it's 1, right? Think of the function y equals x, it's a line, it has slope 1. You can look at this term, right? This term is not too bad. That term is power rule, right? The derivative of x squared is 2x. Power rule, then equals 2. Now, the rest of these terms involve y's, and thus are slightly trickier. So let's look at these other terms. What do I have? Well, here I have, say, this term. What's the derivative of y with respect to x? Well, I don't know. That's what I'm trying to find. So let's just write, literally, the derivative of y with respect to x, and just stop there. That's perfectly fine. That's what I'm trying to solve for, right? So I can't really say more than that at this point. Now, how about this term, this 2xy? Well, this is a product rule, right? I have one function of x, namely 2x, times another function of x, y, right? I don't know what that function is, but on any little intervals of this graph, I could treat y as a function of x. So do the product rule. Take the derivative of the first times the second unchanged, and then add to that the first unchanged times the derivative of the second, right? That's our product rule applied to that product, 2x times y. Lastly, I need to think about what to do with y squared. So what is that? Y squared is a chain rule, right? The outer function is the square. So I do 2y, that's how I differentiate y squared, just ordinary power rule. But there's an inner function here. Y itself is an unknown function of x. So I need to multiply by the derivative of the inner function. What is the derivative of the inner function? It's the derivative of y, but I don't know what y is, so I can't say more than just dy dx. So that's all I say. So that's what I have here, right? So I have here, I used product rule, right? Here I used chain rule. And the rest of these were kind of ordinary derivatives. What can I do next? Well, next, solve for dy dx. This is a bit messy, not crazy messy, but a little bit messy. The best thing to do is put all the terms involving dy dx on the left, while we put all the terms not involving dy dx on the right. So, and how many terms do we have? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. There we go. So we got all of our terms, right? Count the number of terms, make sure you didn't miss one, right? Or at least you missed one and also duplicated one, but maybe there's a lower probability of that happening than just missing one term. So now that we have this, we could factor out dy dx, and we get this expression, which then I can do, because they all had, we very purposefully put all the dy dx's there on the left. So factor out the dy dx, and now divide both sides by 1 plus 2x minus 2y. And now what I can do is now I can say, I have it. I actually have a formula for, this is dy dx. This is the slope of the tangent line at the point x comma y. I have a formula for it, right? So it's not, again, it's not an explicit formula just in terms of x. It involves y also, right? But I do have a formula now for a slope of the tangent line. So now I can take these points that I found up here, and I can get the slopes of their tangent lines by just plugging into this formula, right? So let's evaluate at, say, 0, 0, right? What would I have? At 0, 0, I would get minus 1 minus 0 plus 0 over 1 plus 0 minus 0. That gives me negative 1. So I have slope negative 1 at 0, 0. Let's graph this. There it is, slope negative 1. Right? I could I could do this for all my points, right? I could say for any point, not any point in the whole plane, but any point on the equation, right? Then that actually satisfies the equation. You've got a number for any point in the plane, but it doesn't mean anything unless it's on the actual graph. Let's do 1, 3, right? Let's see what I get here. So I have 1 for all the x's and 3 for all the y's. So what do I get? Let's see, I have -1 minus 6 plus 2 over 1 plus 2 minus 6. So this becomes a slope of -5 up top. Yeah, -7 plus 2, right? And then on the bottom, I have 3 minus 6, -3. There we go. So I get 5/3 for the slope at 1, 3. So I can graph that. 5/3. It's not quite slope 2, but it's more than slope 1, right? So it's a little bit steeper than 45, but it's not quite 2 yet. So it's maybe something like that, right? So this is a slope of, right? This is 1.6 repeating, is 5/3. So there we go. And I could keep doing this. I could keep finding more and more slopes that to accompany my points, right? Well, when you find these slopes, it tells you a lot more about the shape of the graph, right? And let's do one more. Let's do 1, 0, right? So here I would have 1s for my x's and 0 for the y's. So I delete the y terms, but then I put in 1 wherever x was. Right, and I get, what is this, 1/3, right? So very shallow slope at 1, 0. So there's 1, 0. I have a positive but very shallow slope, right, over 3 units just to go up 1 unit. So this is a slope 1/3. Well, now that I have this, I can kind of see what's going on, right? I can kind of connect up the points on the graph, because now you really know how the graph is progressing. It's coming from here, it's coming like this, kind of bounces off this, bounces up this way, right? It has to follow the shape given by these tangent lines, right? And in fact, this graph is a parabola, right? And if you study rotation matrices, right, say in a linear algebra course, that's a great way that you could, in fact, prove. I haven't formally proven this is a parabola, but you can kind of see it, right? Once you have those tangent lines, plotting a few points and then doing those tangent lines, you can kind of see the parabola, right? You can prove it more formally with rotation matrices, but this lets us get the shape at least, right, using calculus. So this is actually a parabola. It's just a rotated parabola. It's not vertical and it's not horizontal. So that's why it didn't look like any of the formulas exactly from college algebra or pre-calculus, right? So there we go. There's a case where we used implicit differentiation, right, to get slopes of tangent lines for a graph where we didn't have an explicit formula. We didn't have a function describing this, just an equation, but we were able to find slopes of tangent lines just the same. So, great, thanks. Rotated conics, they're fun.